So welcome back to another episode of Learning by Doing OpenFOAM. In this episode, we're gonna learn again some nice and interesting stuff. Namely, we are going to talk about coded function objects, which are sort of a special family of function objects in OpenFOAM, which provides us the ability to do dynamic code compilation. Um, and yeah, like the previous video, the inspiration behind this episode is also a question or a problem that was sent in a thread in CFD online website. So we are going to take a look at that without wasting our time. So you see that on 10th of February 2025, quite recently, a user called Sergio basically posted this. Let's read the question first. It says, I have a heat transfer case in which I monitor temperatures in a certain region, let's say heater 1 in code below, presumably this one, at each write interval settled in control.date file. I want to stop the code and write the results before the end time if the difference between the temperature in the current time and the previous moment, which is the current time minus the time interval, is lower than a certain value. For example, 5, capital K, probably Kelvin. But anyways, it doesn't matter when you're calculating temperature differences in centigrades and Kelvin. They're the same. I suppose that I have to write a code and insert it in control.dict file. So he has an idea what the solution might be, and we are going to talk about one possible solution by using coded function objects. And he adds, my difficulty is to write this code, and I don't know where to insert it. Can you suggest me a code and where to insert it in the control.dict text file? Thank you in advance. And this is basically the thing. So it seems like he's using OpenFOAM Foundation version, and the version is 12. And if you remember in one of our previous videos when we had the compilation of OpenFOAM from source, for the Foundation version, we used version 11. I think the general things should be the same between 11 and 12. There shouldn't be too many differences. But anyways, it seems like he's having a conjugate heat transfer. He was also talking about that he has a heat transfer case. It's a conjugate heat transfer. It has one fluid region and two solid regions, metal and heater 1 in this case. And he has its end time at 10,800, but presumably somewhere before that hits, the temperature in the heater region is going to drop or increase in terms of like the temperature within 2 consecutive time steps. At least this is what he assumes that it's going to happen. And he wants to stop at that time that it happens without reaching the max end time of 10,800. And then later he adds 3 days later on 13th, he adds like, can anyone give me an example? More or less like this. And then again, he says how to stop the code and write the results in different It's basically reiterating himself again in the span of 4 days. So the first thing I can say is that it's not gonna, like, repeating your question over and over is not gonna change the likelihood that somebody will basically answer your question. So if somebody has an idea, they will write their answer in there, no matter what. So doing this probably just makes the thread messier without adding any useful data. Anyways, so he did not add sort of any, he has an attached file, it's like a graph or something, I don't care about it. But he didn't provide any sort of tutorial file. So the first thing we need to do is to, by the way, I already fired up OpenFOAM 11, once in this terminal and the other one in this terminal, because sometimes we need to check stuff in the background. So let's go to tutorials. We need to find a case file that basically is similar to what he wants to do. So let's go to multi-region. This is the conjugate heat transfer. And we can take this heated duct. Yeah, this one is nice because it does have the heater in there. So I'm going to my run directory. This is the status, how we left it last time after the compilation. We did some tests on our OpenFOAM installation. So I'm going to copy that heated duct here. So let's go to control.dict and let's take a look at the settings. So first things first, this is foam multi-run, similar to what he wants, and we have region solvers, fluid, one fluid region, two solid regions, metal and heater. So there is, let's say, coherency between the problem and the tutorial that we have here. Stop at end time is okay. End time 20 with a delta t of 1 e minus 3, hell no, we're not going to wait that long. So I'm going to reduce that to 0.01. It's going to be, no, this is like 10 time steps, so let's make it shorter. Let's make it 5 time steps. Adjustable runtime, hell no. I just want it to be time step, and every time step is okay. I'm fine with ASCII right now. And then, oh, I want my time step to be constant. I don't like it to move around. Now let's just run it and see whether this case works out of the box without us changing anything at all. So we got to be patient. It uses SnappyX mesh. I haven't checked the all run script, but presumably it does what it does. Block mesh, snappy, split mesh, and then decompose it. It's a parallel case because we have decompose par and then foam multi-run. And let's take a look at foam multi-run, the log. Okay, you see that we ran it for 5 time steps, and as we predicted correctly, these are 5 time steps that because we wrote the simulation results every time step and we ran it for 5 time steps, so that is why we have 5 of these. It looks good. And if you take a look at, for example, 0.005, there is a heater region and there is a temperature field associated to that. You see the internal field has 16,800 computational cells. That's where the heater is. 16,800. Okay. So now we said we want to talk about coded function objects, but we haven't showed coded function objects at all, and we haven't talked about them. So let's go to OpenFOAM source. Let's go to function objects, utilities, and coded function object. Let's open the header file. The description says provides a general interface to enable dynamic code compilation, and it has some entries, like you can use any of them. For example, code include to include some header files if necessary. And then there's some probes, for example, code read upon function object read, or code execute upon function object execute, and so on and so forth. But how do we need to use that? There is a very, very basic example here. I'm just going to copy that. So let me just, I'm sorry. I'm going to just copy this example, write magu, and then I'm going to go to my run directory, heated doc, system, control dict, and here I'm going to add the section functions, and I'm going to paste whatever I had there. This is write magu. I'm going to change that to like something which makes sense. Let's say heater temperature checker, something like that. The lib is lib utility function objects. I'm going to put some tabs here. The type should be coded, and the code right in here is used. I want to use execute. And what it does here, it basically it tries to get a const reference volume vector field to u, the velocity field. It accesses that through the mesh with the lookup object. For volume vector field we are looking, and the registered name is actually u, and then it tries to basically use the mag, the function mag, to calculate the magnitude of the velocity field, and then it tries to write those results into the drive. So this is a little bit complicated. We want to do something far more simpler. We just want to say hello world, the first thing that basically you learn in programming. So let's save that. That's our basic and the simplest coded function object that we can basically have. Let's do all clean and let's do all run. So if everything basically works out of the box, then we should see at every time step a hello world being printed to the log file of the foam multi-run. So let's just be patient and see what's going to happen. Okay, this is just 5 time steps. It should be pretty fast. I think we jinxed it. Okay, log.foam multi-run, and we have gajillions of errors. So what it says is basically request for object registry region 0 from object registry heated dock processor 2 fail. So this is a multi process or a parallel case run, and this is process 2. It failed, and it says available objects of type object registry are 3 of them available: metal, fluid, and heater. So at first, I thought that this is sort of a bug, because once you test it, like the same or the basic minor design of the function coded function object with other softwares in OpenFOAM, it basically works perfectly fine. And it doesn't work here because the CHD, the conjugate heat transfer, you are basically having different regions, different mesh regions. And that is why that minimal example does not work. I didn't know that, and I thought it's a bug, but I got educated. I got educated in a hard way, and I was told that I need to put region here, and I need to basically write heater. Why? Because, and by the way, he needs to put heater underscore 1. It depends what you write here as the sort of the regions that you have. But anyways, we add this region, and now it should be working, hopefully. All run. So let's see. So you need to, in this case, when you're working with sort of conjugate heat transfer cases, since you have like different mesh objects for different regions, then you need to always, that's a must to put the region there. Otherwise, you get that error that in the object registry, it cannot find the default name of region 0 because you haven't picked it. You need to choose that. So now if I do that, you see now we have finalizing parallel run, and it works perfectly fine. We have hello world. At every time step, we have hello world. Okay, so this was the first thing. But for sure, the question that was asked was not about printing hello world into our log files, but let's focus on his problem. He wants to sort of have access to the temperature in a specific region called the heater 1. So we resolved that issue by saying the region is heater. So now we have access to that region, presumably. And we're going to prove that also. So what we want now is to basically a way to access the temperature. And we already saw in this example how to access the velocity. We can basically do the same. So in that, where was it? In function objects, I think it was in utilities, coded function object, and in this header file. So you see that we had this thing here. Through the mesh, it was trying to get access to the velocity field. So we are going to do the same thing. So we're going to say, I don't care about the type. I'm going to say const auto ampersand. I want just a const reference, and I'm going to call it as a temperature. And I want to access it through mesh, and I want to say lookup object, and it's not going to be a volume vector field, but it's going to be a volume scalar field because we are working with temperature. And I'm going to put T here and my semicolon. So now we do have access to temperature, but this temperature is sort of defined inside that heater region, but I don't need that. I want sort of something which I can work with. I need a single quantity that I can work with. And that is probably a good reason here is to calculate the average temperature of the heater. So what I'm going to do is to basically call a scalar called, let's say, average T. And I want to use temperature. I want to perform a weighted average. And my weighting field, I want it to be the volume of the cells. And this is going to create sort of a dimensioned scalar for me. But I'm interested into the value of that. So I'm going to put a value here. So I calculated the average temperature. So now we should take a look at that. So let's say info, and then I'm going to say average temperature equals to, and then let's go with average T and N line. But we earlier said this mesh is the heater mesh, but we haven't proved that. So let's take a look at another info statement. Let's go with mesh size equals to, and I'm going to go with mesh and n cells. And the next thing I want to basically check is that what is this temperature field? Let's take a look at that. I want to check it with the mesh, whether it is consistent or not. So what I'm going to do here is I'm going to say, let's say T or temperature size equals to, and then I'm going to say temperature dot and size. That's how we get the number of computational cells that we have associated to that volume scalar field. So I have a lot of things here. So let's just clean this. I'm sorry. And let's just run it and see whether what we basically printed will work or not. We have it in the span of 5 time steps. And let's see. And by the way, if you remember, once in the beginning when I ran the case, the temperature field in the heater had 16,800 values for the internal field, if you remember that. That's the number of computational cells that we have in the heater section. Now let's go to log, to foam multi-run, and you see that the average temperature is 300,011, and the mesh size is 4200, and the T size is 4200. So these two are matching. But as I said earlier, the size of the temperature for the internal field was 16,800. I need a calculator. 16,800 divided by 4,200, the value that we got here. If I do that division, it's 4. Does it ring a bell or something? If you remember, this was a parallel run, and we have 4 processes. So 4 times 4,200. So if you take a look at decompose par, if you search for heater, you see that decomposing the heater part, we are left with processor 0 is left with number of cells 4,200. Process 1, 4,200. 2, 4,200, and process 3 also with the same amount of cells. So what we are basically infoing right there as the mesh size and as the temperature size is the local size that they have. So we have the master process and we have all the other processes, and each one of them, they have the same amount of 4,200 amount of computational cells. But then we raise the question that once we are calculating this weighted average, what is this average T? Is it the average temperature that is locally on each processor? Or is it the average temperature that is in the whole heater region? To know that, you can also check the source code. This is that. I already searched for that weighted average. And it says calculate and return weighted average. The definition is at line 591. If you click on that, you see that what it does, it basically, it uses GSUM. And GSUM is sort of that parallel sum. So what it does is basically it multiplies the weight field with the primitive field. Primitive field in this case is sort of the temperature. And then the weight field was the volume of each computational cell. So what it does, if you have so it means that we are calculating the average temperature depending on the size of the volume of that computational cell. So if you have a bigger computational cell, that computational cell is going to have more impact or more influence on the average. This is a volume sort of average that we are performing right here. But it uses GSUM. So it already is using the parallel version of that. So there is communication happening here. And this average T is actually the average temperature inside the region heater, if that makes sense. But each of these, sort of like the mesh size or the temperature size, these are the local data that every process has access to. And once you info it, you basically get the message from the master processor. Although you can also like use the other version like pout to check basically what's going on. So I'm going to delete that, and we can maybe show that. Let's use pout instead of info, and let's print the average temperature. Let's all clean this and all run that, and let's see what we get with this version. So if you're right, and if that gsum is basically the parallel version, then the average temperature that we are getting should be equal for every process in this simulation, right? So we should take a look at foam multi-run, the log file. Okay, so if I say this, you see that this is process 0, it has this average, and process 1 has the same average, process 2 has the same average, process 3 also has the same average. Okay, so now you understand the difference. So let's just delete that as well. We don't need to track temperature anymore. So now we basically managed to access the temperature field. We managed to calculate a weighted average, a way to basically decide which temperature are we going to use as sort of the representing temperature for the heater. And in this case, we are using the weighted average, weighted volume average. So now the next step is to store this value in the current time step. And then in the next time step, we're going to take the difference and compare them together. So let's say I want to have a scalar, and I want to call it as average t, but I want to put old here. If I initialize that to something like, I don't know, some strange value, -10, for example, each time that this function object is basically running, that it's going to basically define it and initialize it. So I need a variable that is sort of consistent and it's not changing between sort of different runs of this coded function object. So I use the keyword static for this variable. So if you don't know what the static keyword is, I think I already made a video in Learning by Doing C++ video series, the static keyword. You can take a look at that one and understand what's going on here. But basically what we are doing here is that we need a variable that is not basically changing throughout different runs of this portion of the code. I mark it as a static. Now I do have that as, now it's -10. So let's say if the average t old is less than 0, then we want to update this average t old. We want to say average t old equals to average t. We update it. Oops. So let's say update old temp. And else we are going to now check for the condition that he wanted. He wanted the difference between this time step and the previous time step to be like greater than, I don't know, 5 or whatever he wants. So now we want to say another if condition. We want to say if average t minus average t old is greater than, he wanted it to be like 5. So let's put 5. Of course, in our case, the average temperature is far less than that, the difference is. So if that's the case, then this means end simulation and write results, right? And if it's not the case, what should I do? I need to update again the average t old. So I'm going to say average t old is going to be updated with average t. That's from the previous time step, right? So this is, so again, I'm going to say update old temp, old temperature. But how are we going to end the simulation here? So by the way, we have like a control flow here that we need to test it somehow. Anyways, so we need a runtime here. So let's go with const auto. Or no, let's not do anything here. I just want to test it. I don't want to confuse you guys here. So we have a control flow here. We have, we check whether the average temperature is less than 0. So the first time it's initialized with -10, so it should be, and we update that. So to make sure that this portion of code is basically running, I'm going to info here that average told negative. Very simple. And I'm going to say end line. And in the next case, we are going to basically, if it's not negative, we are going to check the condition, whether the average temperature, that's the new average one right here, minus the old one, the difference is greater than 5. If greater than 5, we need to stop the simulation, but presumably the differences are far less than that. If it's not, it's going to basically update the old time step. So I'm going to put another info statement here. I'm going to say update old temperature. So this is what I'm going to say. And I'm going to put an end line here. So let's just run all clean and all run and see whether this workflow basically works or not. Okay. And then after that, we need to basically take a look at this time, how to stop the simulation. We have this stop at sort of function. It needs a stop at control, yeah. So let's go to foam multi-run and let's search for negative. You see that the first time it says average T old is negative. That thing is printed. And then if you look for update, update, you see that it updates the old temperature. So this means that the difference in the average temperatures between the old time step and the new time step is not greater than 5. And it is obvious because we printed those averages. It was like 300.001 or 300.002, or the differences were so small. So now what we want to do is to, now we know how the workflow basically works. I'm going to remove these info statements. Now what I want to do is to basically try, again, I don't care about the type. I'm going to say auto and then a reference. And then I'm going to say runtime. And this time I want to get access to time. And through that time, we want to say runtime dot stop at. And then we're going to say foam time. It was stop at control. I think it was like that, right? Stop at control. And then let's say right now. So right now it basically is going to stop the simulation, but first it writes the fields and then stops the simulation. So this is what we want to basically do. And that's it. Like, this is what we want to do, right? Let's go with all clean and all run, and let's see what happens. And by the way, this stop at control is also having these values like end time, no right now, right now. This is the one that we used. Set end time to stop immediately with writing. This is what it does right now. And we have also next write stops the next time data are written. Yeah. Okay, so if we go to log foam multi-run, we see that okay, the problem is very simple because we never are gonna hit this we are never going to hit this condition. So I need to reduce that. I think 0.001 probably should be okay. I think the difference is low enough. All clean, all run. So that portion of the code is never basically running at all. And that was the problem. Because we got all those time steps again written. Yeah, I forgot to change that. So in his case, of course, probably the temperature variations are far more than that. So that condition depends on your condition on your case file. In our tutorial case, the average temperature is not varying that much, at least from time step to time step. Now let's look at log foam multi-run and what do we have here? Did we write any results here? Oh yeah, 0.002. And we have heater, and we have temperature, and it's 16,800. So it actually happened at 0.001 heater and T. Okay, it seems like we can also sort of add that info statement back here. Info average temperature equals to average temp or average T and end line. And so here we updated, and here we also updated. So we can see the average temperature in every time step now. Let's just do that, all clean and all run. It seems like it's working because it stops the simulation at the second time step at 0.001, 0.002. And yeah. So normally it should go up to 5 time steps, right? But in this case, it's not going up to 5 time steps because we put that condition right there. Again, it stops here. And if I take a look at log.foam multi-run, you see that it stops here. The average temperature is 300,003, and this is 300,006, which the difference between this and this is greater than 0.001, right? And that is why it stops the simulation. And it should write also the results. So if I take a look at 0.002, we have the heater. Yes, we do have access to the heater. And if I go back to 0.001, here also I have the heater temperature. Yes. I mean, in this case, we don't have, I mean, probably 0.001 was too small. But anyway, we just wanted to see whether if this condition is true, whether the simulation is going to stop and whether it's going to write the results for us or not. And in this case, it is running the results and it is also stopping the simulation. So we are basically fine with that. So there we go. This is basically how you can use a coded function object to solve the issue that this user had. And I hope you learned something from this video and hope to see you in the next one.